All right, so I want to answer these questions that Jordan posted, 25, 27, 29 from 7.5. Let's take a look. So 25, 27, 29, they're all about these partial fraction type of things. And his question specifically was like how to find the constants. So let's run through them. So I've written down 25 here. So 2x squared minus 10x plus 4 over x plus 1 times x minus 3 squared. Okay, so both of these factors in the denominator are linear factors, and this one is not repeated, right? But this one's repeated twice. So the way the partial fraction decomposition is going to look is you're going to have one copy for the x plus 1. So you're going to have just an a over x plus 1. Then you're going to have two copies for the x minus 3. One of them is just going to be x minus 3, and the other one is going to be x minus 3 squared. Okay? So this is what you have to do whenever you have a factor that's repeated, is that you start with that factor to the first power, and then you do that factor to the second power. If it was repeated like 5 times, you would do b over x minus 3 plus c over x minus 3 squared plus d over x minus 3 cubed plus e over x minus 3 to the fourth plus f over x minus 3 to the fifth, right? But for this one, this is as far as we take it. And then just like the solutions that the solution that I posted above this question, I mean, you're going to clear the fractions by multiplying through by the denominator. Here the x plus 1s will cancel. You'll be left with x minus 3 squared. Here one of the x minus 3s will cancel. You'll be left with an x plus 1 and an x minus 3. And here both of the x minus 3s will cancel. You'll be left with an x plus 1. And the idea is that you can equate coefficients, right? Like when you expand all of this out and then collect all of your x squared terms, you're probably going to have like an ax squared and a bx squared, not a c. So then you know that a plus b has to equal 2, right? And similarly, like with your x terms, you know that whenever you expand it all out, whatever you get, like, a plus, negative 3a plus whatever b plus whatever c, it has to equal negative 10. And so you get this system of equations where you can solve for a, b, and c. But an alternative way to, and it doesn't always work, but it can sometimes help you to narrow things down, is to just plug in values for x, plug in convenient values for x that will cause a bunch of stuff to cancel off. Like in this case, I know that if I let x be 3, this is going to be gone, this is going to be gone, and I'll be able to solve for c. Right? So if I let x be 3, then 3 squared is 9, times 2 is 18. 18 minus 30 would be negative 12. Negative 12 plus 4 would be negative 8. So I get negative 8 equals, that's gone, negative, or sorry, 3 plus 1 is 4. So I get 4c. So negative 8 equals 4c. Which means that c is negative 2, right? I can do the same. If I let x be negative 1, that'll be gone, I'll be able to solve for a, right? I'm going to get 2 plus 20 is 22, plus 4 is 26, equals, and here negative 1 minus 3 is negative 4. Negative 4 squared is 16. So I get 16a. And then that's gone and that's gone, right? This is not very nice, and I wonder if maybe I made a mistake in my arithmetic. I'm going to double check it. Negative 1 squared is 1, times 2 is 2. Negative 10 times negative 1 is positive 10, so I get 2 plus 10 is 12. Plus 4 is 16. I don't know why I said 26. It should be 16. Anyway, 16, that's much nicer. Anyway, so A is 1. Now, getting B is a little more difficult because if I plug in 3, that'll be gone. If I plug in negative 1, that'll be gone. But if I need to be able to solve for B, it's like nothing else is going to help me. I suppose I could plug in like 0 or something. Since I already know A and C, it doesn't matter that they're not going to be canceled off because at least it'll help me solve for B. that might be a nice way to do it, right? So I'll just let x be 0. Then we're going to get 4 equals, negative 3 squared is 9, so 4 equals 9a. Here we're going to have 1, negative 3, so minus 3b. And here we're going to have c. But I know that a is 1, and I know that c is negative 2. So 4 equals 9 minus 3b minus 2. So 4 equals 7 minus 3b. Can subtract the 7. I get negative 3 equals negative 3b, so b is 1. And there you go, right? So, so this original integral now is going to be integral of a over x plus 1, that's 1 over x plus 1, plus b over x minus 3, that's b was also 1, so plus 1 over x minus 3, and then c over x minus 3 squared, so that would be minus 2 over x minus 3 squared dx, right? And then, you know, these things are just natural logs. This thing, you know, you could do a u substitution or whatever, and then it's just like a 2 over u squared type of situation. So like it's not complicated to solve at this point, so I'm just going to leave it there. One thing that I will say is that as far as the natural logs are concerned, is that you know, you're going to get ln of absolute value of x plus 1 plus ln of absolute value of x minus 3 plus, what is this even going to be? It's like 2 times u to the negative 2, so it's going to be 2u to the negative 1 times 8, so it's going to be plus 2u, it's going to be plus 2 over u, where u is x minus 3, so it's plus, so it's going to be plus 2 over x minus 3, right, plus c, something like that. I could be wrong about this last term because I was kind of doing it in my head, but I think this is what you end up with. But what I wanted to point out is that here, whenever you have a bunch of natural logs, your book likes to throw these all together using properties of logarithms like the product rule, quotient rule, all that stuff. So like in this case, since you're adding two logarithms, that's the same thing as throwing them together under the same minus 3 under the same logarithm like that. And then your book might even actually like multiply this out, right? So it might say this is like x squared minus 3x plus x is minus 2x and then minus 3, right? So it might do something crazy like that even, right? But this is still the correct, this is still a correct answer, you know what I mean? This is just like a slightly different version of the same thing. But you know, it is a little bit frustrating, but you just have to kind of get used to forcing your answer to look like what's in the back of the book. I mean, if possible, right? So anyway, that's 25, and I have a feeling like that's a lot of the trouble. Like if you're having trouble with this and like your answers aren't matching what the book has, I have a feeling that this might be more of an issue than actually the partial fractions part of it itself. I could be wrong about that, but that was 25. 27. I don't know if I'm really going to go through all of these, but let's just talk through the partial fraction part of it. So for 27, okay, so for 27, you have a linear, so I'm just looking at the denominator, right? But you have this linear factor that's repeated 3 times. So the partial fraction decomposition is going to be of the form a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. Okay. And then, you know, you solve for a, b, and c. On that one, you're probably not going to be able to do any of the tricks that I did before with, like, you know, let x be negative 1. If you let x be negative 1, then a, b, and c are all going to get canceled off, and it's not going to do you any good. So I think with that, you're just going to you're going to have to equate coefficients. Maybe this would be a good one to go through, but But let's talk about 29, and then maybe I'll come back and do 27 to show you what I mean. But 29, here we've got a linear factor and then a quadratic factor. And this quadratic factor can't be factored any further over the real numbers. You can factor it over the complex numbers, x plus I times x minus I, right? But you can't factor it over the reals. So this is an irreducible quadratic over the reals. And so the way we deal with that is a little bit different. But the linear factor here is just going to be an a over 4x minus 1. And then the quadratic factor is going to be a bx plus c over x squared plus 1, right? So the partial fraction decomposition is going to look like a over 4x minus 1 plus bx plus c over x squared plus 1. And then clear the fractions, equate coefficients, blah, blah, blah. But let's go back and actually maybe work out 27. So I'm going to write this thing down. We've got integral of x squared over x plus 1 cubed dx. Okay. So as I said, this is going to look like, a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed dx. And I guess if I ignore like the integrals and I just focus on the rational expressions and I clear the fractions through, I would get, x squared equals a times x plus 1 squared plus b times x plus 1 plus c, right? Which is kind of an odd thing, I guess. Actually, I could solve for c pretty easily. Let x be 0, and then c has to equal 0. So that's kind of nice to know, right? Or not 0, I'm sorry. X has to be negative 1. Let x be negative 1. Then you get negative 1 squared is positive 1. A is going to be gone, B is going to be gone, and you're going to get C. All right, beautiful. From there, I think solving for A and B, it's going to be a little trickier. Yeah, so let's, like nothing really jumps out at me at the moment to be helpful here. So I'm just going to equate coefficients. I'm going to say x squared equals a times x squared plus 2x plus 1 plus bx plus b plus c. So x squared is ax squared. Well, there you go. So a has to equal 1, right? Plus 2ax plus a plus bx plus b plus c. I'm going to take it just one step further, right? So I got ax squared plus 2a plus b x, and then plus a plus b plus c for my constants, right? So what this tells me is that, if I equate coefficients, a has to equal 1. 2a plus b has to equal 0, because I have a 0x over here. And then a plus b plus c also has to equal 0, right? So these two equations together can be used because I know that c is 1, but actually I know that a is 1 as well, right? So I can just say 2 times 1 plus b equals 0. So b is negative 2. And there you go, right? So that's that. That's how you deal with these partial fractions. Again, I suspect that probably what's actually giving you more trouble than the partial fractions themselves is just this thing that you haven't quite realized that, oh yeah, like properties of logarithms, right? Like if you've got some crazy ln of x plus 3 minus 2 ln of x plus 7, plus 5 ln of, I don't know, 2x plus 2. I don't know, something crazy. It's like you can throw all of these things together, right? It's like, so you use the power rule. right? Actually, that one still needs absolute values. You know, and then you can be like, oh well, yeah. I mean, so here's a product rule, and then here's a quotient rule, right? Because I'm subtracting. So this really, at the end of the day, is like x plus 3 times 2x plus 2 to the 5th over x plus 7 squared plus c. And then if you really wanted to go crazy with it, it's like you could expand all of this stuff and drive yourself crazy. But yeah, so that's that. Hopefully there's something there that is of use to you on those problems. Give it a watch. Let me know if you're still kind of struggling with these things, and maybe give me a little more guidance on like where it is that you're having trouble.